let's do a brief introduction to the concept of continuity for functions. I've got a graph of a function up here, and in a minute we're going to start playing with these points to investigate the idea of continuity. But I just want to go ahead and start with the definition to connect to that. We've seen the definition already, and I didn't really need that. There we go. It's that f is continuous at a if the limit as x approaches a of f of x. It has to exist, and the value has to exist. That comes out really weird in math mode. Let's just take that out of math mode. That's silly. Okay. There we go. There we go. Okay, so it's f is continuous at a if the limit exists, the value exists, and they're equal. And we say that f is continuous on a whole set if it is continuous at all a in the set. That's pretty natural. You just say it's continuous, meaning, okay, it never fails this test, no matter what a you talk about. So let's look at how this picture explicates that, and then we'll think about the intuition behind that a little bit more. So let's say I'm comparing these points. We've got a equals 0.5 for one example and a equals 1 for another example. At a equals 0.5, if I look at the limit of f of x as x approaches a, so that's, if you want to think of this as a variable point, and x gets as close as I can get to a, and what I want to do, so I'm setting this to be small, this width to be small, to make the limit make sense. To take the limit as x goes to 0.5, and then I'm looking at what happens to the y values, because that's what is important about the function. What happens if I give it a certain input, what happens to the output? That's what functions are all about. And what I notice is the output values are getting really, really close to the output value that I would get right at 0.5. And so that's saying that it's going to be continuous at that point. Now over here, I'm looking at if a equals 1, this looks drastically different, and indeed it is. If I look at the limit from the right of this function, these values are, as x gets very close to 1, these values are not getting anywhere close to the value that they should be getting, which is, I don't think I put it in here, but it's equal to 1. Okay? And so the y values are way, way, way far. Now, if I actually came in from the left, it would be okay. So this is an example of a function that's continuous from the left at 1, but not continuous from the right. And so the limit of those y values is getting close to 1. Okay. So a little bit more about the intuition behind the exact definition, and then there's some more intuition about that's a little bit rougher. The intuition, basically saying, restating this in words, is that a small change in the input should only produce a small change in the output. And that's really an incredibly important thing about continuity. That's really what it's about, usually. A small change in the input should only produce a small change in the output. How does that have to do with this limit definition? Well, I start with a equals 1, and then I purposely walk off a little bit to a different x that's close by. And that was the x that we were looking at if we wanted to calculate this limit of limit x goes to a of f of x, this limit here. That says, don't put x equal to a, but don't put it too far away. Make it really close and see what happens to the y values. Those y values are definitely have a trend. That trend is towards -1. And so when I put in values that are a little near 1, but not quite at 1, I get things that are -1. Whereas if I put 1 exactly in, I get +1. And that says that a small change in the input, changing from like 1 to 1.01 or something, has produced a drastic change in the output. Okay, and so continuity, let's just make it clearer. This is what continuity means. Okay, let's contrast that to this guy again. Here, this is supposed to be a point as continuity. If a equals 0.5, then this is supposed to be a point where the function is continuous. And indeed, if I start at exactly at 0.5 and I move it off a little bit, the y values don't change very much. The x, they change a little bit, but when x changes a small amount, down here, the y values change only a small amount up here. And that's a point of continuity. This is really how continuity is practically useful is that small changes in input should only produce small changes in the output. Okay. The other thing about intuition that you often see, which is really useful, is that a function is continuous on some interval, let's say, if I can draw the graph without lifting the pencil, without lifting the pencil. Okay. This is pretty rough, and there's some cases of really weird functions where you'd really kind of be confused about, can I really do this? Is it continuous? But mostly, this covers most cases. And that's how you tell at a glance, basically, if something is continuous. But it's better to look at this, because this is actually why continuity is important, and we'll look at some examples of that in applications. And then to really test it, you want to go back to this definition. Okay, but this is really a good thing to know. And I'm going to split this into two to make them small. So I'll stop right now.